Hey, hi, Afnan.
Good afternoon, sir.
Yeah. So you have only this MLT tomorrow, right? Or you have other OPPs also?
I have DBMS also, sir.
Oh, okay. Two exams tomorrow.
Yes, sir.
Okay, okay.
So I think in the morning, DBMS, and in the afternoon, there is MLT.
Oh, okay.
Yeah.
We'll just start in 2 minutes.
So will we get the grading pattern by today?
Yes, so I'll just tell you roughly what is going to happen, and I think you'll also get it. You'll also get that mail soon, I guess. Okay, so the exam will have like same number of questions like last time, right? 7 questions. The only thing you have to keep in mind is that they all have different marks. So last time also we planned that, but we didn't inform it in advance. But this time, what will happen is that the instructions will have the distribution of marks, 100 marks. So the paper is out of 100 marks. It will have the distribution of marks for each of the 7 problems. And at the top of each problem also, the marks will be written in bold. So you will know, even when you're solving, even before you start solving, you'll know which problem carries how many marks. Right? So roughly they are all same. It's not like 700 by 7, but it's not too different. So, but there will be 7 questions, and all of them are mandatory. Okay, so there are no choices. Please note that it's not like you have to do best 5 out of 7. It's like you have to do all 7 if you want to get the full 100. Right? So yeah, out of 8 weeks, you have to answer 7 questions. So the questions will be distributed across the weeks, and yeah. So for those who join late, there will be 7 questions in the exam, and questions will carry different marks. So each question will carry a different number of marks. The marks will be written clearly in bold letters at the beginning of the question. Right? So right before the problem begins, you will see how many marks that problem carries. And also in the instructions, the grading policy will be given. So grading policy is basically this distribution of marks, right? Which question carries how many marks? That distribution will be very clearly mentioned in the grading policy, in the instructions. So one suggestion from my side is that, see the questions, of course, some questions will carry more marks, some questions will carry less marks. So that is our perception of the difficulty of the questions, right? So 2 or 3 of us sitting here think that this question is more difficult than this, and therefore we have given more marks. But I urge all of you to go through all 7 questions. For some of you, say it's a particular question, particular topic you might be more familiar with. So even though it carries more marks, you might be very comfortable doing that question. So please make it a point to read all 7 questions and then start attempting the problems. Okay, so that is about actual questions. Yeah, so will we get questions which ask us to write an entire ML algorithm? Yes, potentially yes. But you won't see you you won't have to stick to classes, right? So you won't ask you to write a class, let's say a class called svm that has these many methods and these many attributes. It won't be along those lines, but you must know if you're asked to write an svm algorithm, an svm from scratch, right? You must be able to do that in your own way, right? It's not necessary that you should use classes, or you can use whatever functions you want, but you must be prepared for that. Okay, any other questions regarding the exam?
Sorry, sir, I just joined late. Is it syllabus 5, week 5 to week 11, or is it week 5 to 12?
5 to 11. 12 is not included.
12 not included. Okay.
Yeah.
Okay, thank you.
Okay, so that is, so the exam, if you know the concepts, as I said the other day, right, if you know the concepts, then it is kind of very easy, the exam. The execution part, you have to be careful how to convert it to numpy. That is what we'll be doing today. I'll try my best to address some of these points, but I think most of it you already know, right? So yeah. So svm kernel is not, I won't say it is not important. It's good to know. svm kernel code we didn't discuss, right? So it's not really a part of the syllabus. The kernel part, right, is soft svm is still there, hard svm is still there, but the kernel svm is just for your just out there, right? It's not necessarily included in the grading.
Sir, a doubt here.
Yeah.
So when we're using NumPy, there are also a lot of like randomized operations sometimes. So when we're coding the algorithm from scratch in the OPPE, would there be like seeds mentioned, or like particular way of initializing the parameters?
Yeah. So
like that.
Correct. Yeah, that will be mentioned. So if you have to initialize, say, some weights, then what initialization is you have to follow is something that will be given, right? So that part won't be left hanging. Okay, so that is something we have ensured this time. So will we be able to see our own output in public test cases? Yeah. So this time, we haven't been able to do it for all 7 questions, but for at least 3 questions, you'll be able to see what input your program is getting and what output you are expected to print. So 3 out of 7, we have made sure that the test case area is kind of makes sense for you all. So it's not just like simple messages. Maybe not 3 out of 7, 2 out of 7, but that's the way it is. So building trees.
Just the build tree code alone wasn't. It's not amply clear. We didn't discuss it with solvent instructor as well as in the lecture, and then the code looks a little. I mean, certain parts look a little tricky to me, at least from the pandas part of it. Okay. I wasn't sure whether that's something we need to look at it.
Is it the sklearn.decision tree regressor, that part, is it?
Yeah, the sklearn is used, but then this build tree actually takes a model as an input, and then builds the tree based on that. It's a recursive algorithm, so the algorithm itself is
algorithm, right?
Yeah, the algorithm is recursive. So that the structure of it is very clear. Just that some portions of it are not. I mean, at least to me, the pandas part of it is not very clear to me. I wasn't sure how much of focus we need to give to that code. Because in the solve with instructors, we had covered a lot of the components to build a tree, like finding the best attribute and those kinds of things. So I think all that is reasonably well covered. It's just the build tree code I wasn't sure. So
okay, so I think Parth and someone else, who else has created this? You maintain repos, right? Do you have like sufficient explanation for this part in your code basis?
So I've not coded the code given in the lectures. I've coded the cart algorithm, not ID3.
Oh, okay. Someone else also shared the repo, right? Do they have?
Yeah, I have the repo. I don't know if I have the sufficient explanations though. I'll check and let you know in 2 minutes.
Okay, sure. Okay. So Kaushik, maybe you can take a look at those that repository, Vishwajit, whatever he has shared.
Sure.
Will be of help. Yeah, if Nitin had been here, like, he would have been able to, but unfortunately today he was not able to join. So
No worries. I'll
Yeah.
take a look at that. Thank you.
okay, so yeah, see how many questions are easy. This easy, simple, all that you will know based on the distribution of marks, right? So that we have, as I said, we have given it in the grading policy. It will be available in the instructions section, right? So see, all questions will be more or less of the same difficulty. Some may be little more difficult. So
Sir, can you tell the grading policy now so we can understand from beforehand?
no, see, it's very simple, right? 7 questions with slightly here and there, you will have different number of marks for different questions. That's all. Right? More than this will not, I think, help you. That's what I feel, right? 100 by 7, roughly, you can think about it that way, plus or minus some delta here and there. Right? So you will anyway have to see, the way I see it is you will anyway have to solve all 7, right? At least if you want to get the passing mark of 48, at least 4 questions you will have to attend. So that's how I see.
Okay, sir.
Okay, so yeah, we'll just carry on. See, I don't have a proper plan per se revision because the one big disadvantage I have is, since I was part of setting the question papers, I have this tendency to discuss the questions, even if it is in an indirect way. I end up discussing some aspect of it. So what I will do is I will not go too much into the theory part of MLT. I'll just focus on NumPy and how you can translate mathematics to NumPy code, right? So that is what I'll be focusing on. If you have any specific questions, I can always try and answer them, but otherwise we just go over aspects of NumPy which will help you in the exam. Okay, so I'll keep referring to what's important, what you need to note, and that's how we do it. So one observation that I have seen, I am not sure how far I am right in this, is there is a tendency to use 2-dimensional arrays for all objects, right? So NumPy has clear distinctions here. So in our course we typically use 1D arrays for vectors and 2D arrays for matrices, right? So in the exam also we have tried to follow this convention. So whenever you see a data matrix like this, right, it will always be a 2D array, something like this, right? So this has 3 features and 2 training examples or 2 samples, right? So this is something you have to always remember. It's 2-dimensional, and of course shape is quite clear in this. And if you have, let's say, a vector, right, you want to represent using NumPy, it's always going to be this way, right? So it's always going to be n-dimensional, right? And when we say in the question that B is a vector of some shape, it will always be n comma nothing, right? So it's this actually represents a single 1-dimensional tuple, right? It's a tuple of size 1. I hope you're all aware of that, right? So in the question, whenever you come across something like this, right? So B is a vector of shape n comma. It doesn't mean that we have missed out on this particular aspect. It just means that it is a 1-dimensional array, NumPy array, to represent a vector, and it has only n elements in the first dimension, and there's only one dimension to this particular array, right? So all vectors are going to be 1D arrays, and all your data matrix and all the other things are going to be 2D arrays. Okay, please note this distinction. You could also do something like this. I don't know how many of you do this, but there is maybe a tendency to do something like you reshape it as -1, 1, right? So it's not wrong. So this is the same. I have to equate it to B. So this is the same vector. Okay, the contents are kind of same, but its shape is 3 cross 1, right? So you treat it like a matrix, but with 3 rows and 1 column. It is not wrong, but I strongly urge all of you to stick to one-dimensional arrays for vectors, right? That's always safe. So that is one point which I wanted to convey. Next one is related to this. So matrix multiplication is easy, right? So this is just, you have two matrices x and y, x at y is their product, so you don't have much problems here. But when it comes to matrix vector multiplication, right, again there is some tendency to think that I can only multiply a matrix and a vector if this y is of shape n cross 1. Okay, so that is not needed. So I'll just again show an example with this case. So you have your data matrix, and let's say you have a weight vector like this, which is, so how many elements should be there in the weight vector? 3, right? So let's say 7, 8, 9. That's the weight vector. Now xw will work perfectly fine, right? Even though x has shape. What is the shape of x? X is, notice the shapes of these two. This is 2 cross 3 and this is 3, right? This is not 3 cross 1 per se. Okay, but still the matrix multiplication will go through without any hassles. Okay, this is something you have to understand.
But in this, broadcast will not work.
Broadcast.
Broadcast will also work, yeah, because the last dimensions are the same.
Okay, last is mentioned. Okay, but if it goes 3, 2, and then 3, then broadcast will not. Then we'll have to reshape, right?
Or 2, 3 and 3, 1, I think broadcast won't work. Oh no, even that will work
3,
because the
2
last
will
dimension
work.
does one, correct?
Yeah, so see the point I'm saying is this need not be 3 cross 1, right? So let's see both these cases. Let me call it, say, product, right? Now if I print the product, what shape will it have, the product? Will it be 2 cross 1 or 3 cross 1?
Only 2.
It will be only 2, right? So that's the point you all need to remember, right? So P will only be a single dimensional vector, and this is very convenient, right? Why is this convenient? If you think about linear regression, logistic regression, any of your models which have weights W in them, this will directly return to you some kind of a vector of predictions, right? So instead of this, had you used something like this, right, where W is not 3 cross, sorry, it's not 3, but let me reshape it, 3 cross 1. Okay, so if you reshape W to 3 cross 1, this is kind of more convenient to your the way you think about matrix multiplication, 2 cross 3 into 3 cross 1, but you end up with a 2 cross 1 vector, a 2 cross 1 matrix, right? Which is not very appealing in my opinion. It should be a vector, right? Unnecessary dimension you are adding. So the summary of this second point is that you can multiply a matrix and a vector right? And this vector is, it's enough if this is a single dimensional numpy array. You don't need it to be a 2D array where the second dimension is 1. Okay, I hope you all got this point, what I'm trying to say. Okay, so that is one. The second part where you will, any questions? Yeah, so the second part where you will face some kind of problem, or you could potentially face problems, is broadcasting, right? So I don't know if this is, the mental model of this is quite clear to you, what is happening. But from the perspective of our course, you just need to know these two rules of broadcasting, right? So there are two cases where you need to be careful. Adding a row vector to a matrix, that is case one, which you need to be aware of. The second is what could be the second case?
Adding a column vector, sir.
Yeah, adding a column vector to a matrix, right? So these are kind of slightly different. And okay, so let me, maybe instead of doing it like this, so there are going to be 16, say 20 numbers, and I am reshaping it as a 5x4 matrix, right? Will this work? Okay, right. So this is X 0, 1, 2, 3, 4. So this is a 5x4 matrix. Maybe I'll make it 5x3. Okay, so this is, let's say, one matrix, right? And let's take the first case. You want to add, you want to add some row vector to this matrix. Let's call that row vector, say R, right? R stands for row. So I'll make it explicit here. Let's say I want to add this particular 5, 1, 3, right? This is this row vector I want to add to each row of the matrix. Okay, so how would I do this? What would be the, sorry, I am not able to hear you. It's very feeble.
Just X
X plus R.
Okay, it's just X plus R, right? So let's see if that is correct. Okay, so there are no problems when you want to do this, right? So this is okay, so this is X and this is X plus R. So notice that both, this is 5 cross 3, right? So this is 5 cross 3 and this is 3, right? So this has shape, the row vector has shape 3. So whenever you are, let me write this down explicitly, X is 5 comma 3 and R is 3, right? So one of the rules that you have to keep in mind is, whenever the last dimension of two arrays match, right? Here 3 is the last dimension. This is, there is only one dimension here, and that is 3, right? And whenever they match, you can go ahead and add those vectors, sorry, or those numpy arrays, right? Broadcasting rules will apply here. So this is, these two numpy arrays are compatible for broadcasting. Okay, so when you write X plus R, it means R will be added to each row of X. Okay, so I hope this is clear to all of you. Now, if I just slightly change this, I'll take the whole thing, but rather than adding a row vector, we'll add a column vector. Okay, so we are now adding a column vector to a matrix. The X matrix remains the same 5 cross 3, but this I am changing it to a 5-dimensional vector. Okay, so I'm going to run this, and I want you all to become familiar with the error message. So whenever you see a value error which says that operands could not be broadcast together with shapes 5, 3 and 5, it means that you are trying to add 2 numpy arrays which are not compatible for broadcasting. Okay, so if you look at the numpy rules for broadcasting, the last dimension is 3 here, the last dimension is 5, so you cannot add them. Okay, to fix this, what do we do?
Reshape.
Take transpose of it.
Reshape.
Yeah, so reshape is the one. So transpose will not work here, right? Because, okay, you can transpose maybe X, but if you're talking about transposing R does not have a transpose, right? Or the transpose of R is itself. It's just a only array, right? There is no concept of transpose for that, right? So yeah, this is again an important point. So see, this is R, right? R is what? In this case, it's some 5-dimensional vector, right? So if I do R dot transpose, I won't get an error, but I'll just get the same vector again. Okay, so one way to fix broadcasting is to make the last dimension 1, right? This is another rule. If either the last dimension should be the same. If they are not the same, the last dimension of one of the arrays, if it is 1, then those two arrays are compatible for broadcasting. So I will do that by reshaping this as -1, 1. So R will now become 5 cross 1. Okay, now this vector has been added to each column. Okay, so where does this come up? It will come up in multiple algorithms. You will see this coming up, right? So where you have to add one column to each element of some training sample or things like that, or you want to subtract or find the distance between 2 vectors, right? And you want to do this for all vectors in an array. In such cases, you will have to resort to broadcasting.
So Karthik, why we can transpose here instead of the reshape?
As I said here, right? R, I cannot transpose R, or I can transpose R, but it doesn't make sense, right? Because if I try to do R transpose, see, R is this. R is a 3-dimensional 1D array which has 3 elements, right? So this is R. Now, if you try to do R transpose, it is the same thing, right? Because there is only one dimension or dimension to it. So transposing it is not going to help.
But we can transpose X.
X, yeah, X you can. Yeah, that is correct. You can transpose X, R, and then transpose it. I mean, do it back, right?
Could you please show what R looks like after the reshaping?
Yeah, so after you reshape it, so let me take it out. So this is what R looks like before reshaping. So it look like this, right? So you are reshaping it as a 5 cross 1 array. So 5 rows and 1 column.
All right, thank you.
Okay, so that is with regard to broadcasting. The fourth aspect which comes up in many algorithms is the idea of axis, right? So axis has been a point of confusion for quite some time. So I think about it this way. Let's again take and reshape it as 5,3. So by the way, reshaping is not an in-place operation, right? So what I mean by that is, if I do x equal to this, x is now a 5 cross 3 array, right? So now let's say I do x dot reshape of 3, 5, right? I'm simply reshaping it again. So if I now print x, nothing happens, right? Because this reshape did not happen in place, right? You have to reassign it in some sense. Only if you reassign it will the change get reflected in x. Okay, so in case some of you try to do reshape and assume that it will happen there, then and there, it's not going to happen.
Can you please repeat this reassign concept again, please?
See, this is x, right? So x is some array. Now, let's say you, for some reason, you want to reshape it. Let's say you want to flatten it into one long vector kind of thing, right? So it's like so something like this, right? So you have a 15 cross 1 array and you want x to be this, right? So unless you say x is equal to x dot reshape of -1, 1, x will not contain this reshaped array. So the point I was trying to make is that just calling the reshape method on x is not going to replace it in place, right? In place. So if I now print x, it will still be that 5 cross 3 array.
Okay, so after reshaping, I have to assign it some other variable.
Either some other array or some other variable or the same variable name if you want. If it's fine with you.
Okay, yeah, got it.
It's like sort and sorted for a list.
Exactly. L dot sort and sorted of it. The difference is the same as.
Even if we do transpose also, will it change the property?
No, I think transpose is also not in place. So if you look at it, x dot transpose is not an in place operation. So you have to reassign it to a new variable or do something like x equal to x dot transpose for it to get affected.
Yeah, this is always even also a best practice.
Yeah. Okay, so axis thingy, right? So the axis part is, there are two use in our course, at least we have only 2-dimensional arrays. So you can only consider two axes, 0 and axis equal to 0 and axis equal to 1. So many times what will happen is you may have to sum along one axis, right? Say sum along. So before going to the axis, you may want to sum along the rows or sum along the columns, right? So sometimes this rows and columns convention can get confusing. So the way I remember the axis business is, let's say I want to sum all these horizontal vectors, right? All these horizontal vectors and then get that result as a single horizontal vector. So it's like I want to sum from top to bottom, right? It's like you are sitting on top of this NumPy array, right? So that is what I mean. So if you sum from top to bottom, what you will get is 0 plus 3 plus 6 plus 9 plus 12, and then this whole thing and this whole thing, right? So how do you do that? What is the axis value that you?
0.
This is 0, right? So top to bottom is 0. Let me also print x for so that it's clear. Okay, so your it's 21, 27, 30, right? So your top to bottom is axis equal to 0. Left to right is
1.
axis equal to 1, right? So
Sir, is there any concept of axis greater than 1?
there is, if you are talking about three-dimensional arrays, right? So once again, I just print this value so that it's printed. Yeah, so this is axis equal to 1, right? So I hope these two sums are clear, or these two operations are clear. When you want to do axis equal to 0, when you want to go down, axis equal to 1 is when you want to go right. If you want to collapse the array from left to right, you use axis equal to 1. If you want to collapse the array from top to bottom, you use axis equal to 0. And this need not be sum, it could be max, sum, argmax, whatever. Yeah, so there are cases when axis can be more than 1. So say you have an array like this, right? So np.zeros of 10, 20, 30. Okay, so if you visualize this, this will be one huge three-dimensional numpy array. This is often used in the case of images. So for example, you have your mist digit data set, right? So let's say you have 100 images, which are of size 28 cross 28. Okay? Then you would have to deal with three-dimensional arrays. Right, so it's actually nothing very complex. So x of 0, for example, would be image number 0, right? And its shape would be 28 cross 28. So if you want to do something like find the maximum pixel value across the images, right? So I don't know. I mean, I'm just thinking out loud here. So you might do something like axis equal to say 0, or if you want to find the maximum across all the images in this particular index, then you might do axis equal to 2, something like this, right? So just giving you a very rough idea, but axis equal to 2 is possible, provided you have three-dimensional arrays.
So Karthik, axis is more than 1, that is beyond our OPPE.
It is beyond the scope of our course. Yeah.
So, sir, here you were talking about digit data set available in a scalar.
Yeah.
So in that case, we have to use 3 axis, right?
3 axis, yeah. It comes as a, I don't know how, I think it comes as a three-dimensional numpy array where first dimension corresponds to the image number, image index, right? And the other 2 dimensions correspond to the pixel value. So if you have a three-dimensional array like that, x of I, j, k would mean the following, right? So it will mean in image number I, what is the value of pixel at location j comma k. So that is what it will mean. So for example, x of 0, 0, 0 would mean in the first image in your data set, what is the top left pixel, something like this, right? Top left is 0, 0. So if you have, let's say 0, 0 minus 1, then it would mean top right, right? Things like this. That is 3D numpy arrays.
Excuse me, sir. May I ask something?
Yeah.
So when we are summing this matrix in the above example, x is equal to 1 or 0. So it also gives back the one-dimensional vector and not as like 2 cross 1 or like that, 5 cross 1 in this case, right?
Exactly.
It's just that it's just 5.
Yeah, that's a good point. So when you do this operation, it becomes a vector. Yeah.
So is it the case with all those numpy operations, or are there operations such that they give back a matrix also, right? I mean, in that sense.
See, most of the common operations like max, sum, argmax, these 3 are the ones we use, right? All of them are going to return vectors, right? I am not sure if there are other operations where I don't think so, right? See, the whole point of having this axis argument is to get some kind of a summary information across one axis. So for example, when you do axis equal to 1, you are getting some summary information across the columns, right?
Right.
So at least the operations that we use, sum, argmax, max, min, all these are such kind of operations which collapse the information contained in one axis into a single number, right? So I don't know if there are other operations which kind of retain the shape of the array as it is. I am not sure, but yeah.
Okay, understood.
Okay, so now that is axis, right? So useful methods for arrays is what we have next. Useful methods for arrays. See here, typically what happens is NumPy offers several ways to do several things, right? So if you take the same case of, say, with that 5 cross 3 wala, so you look at that array and you could do transpose in two ways, right? So you could do np dot transpose of x, right? Which is not wrong, but NumPy has a very simple way of doing it. You can just do x dot t, right? And in the interest of time and clarity, please go for this, not just during exam, but even afterwards, right? So I don't know about the computational complexity of this versus this. That is something I don't know, but you can explore that later. But from the point of view of exam and even later on, x dot t is far more clear than np dot transpose of x, right? So there is one extra cognitive load here. You have to read so much, and then it may seem like very little, but still always it's easier to do x dot t. Okay.
Sir, for some example, one form work, another form do not work. I'm not able to recall where it happened, but sometimes I observed that.
Is it? Okay, at least in my experience, I have always been able to get away with x dot t. If you can think of, if you can, recall that, please share it. We can discuss that.
Okay, sir.
Okay, so the other, see, these are all methods. By the way, these are all array methods. So I hope you see the distinction here. This is a NumPy method. Transpose is a method of the NumPy library. Here, or rather the NumPy module, but here capital T is a it's not even a, is it a method? It's not a method, I would say, but yeah, I think it's, yeah, you are right. It's an attribute of the NumPy array object, right? Now, likewise, you have sum of x, right? You have np dot sum of x. You don't need to do np dot sum of x really. You can just do x dot sum. Of course, that will end up summing the whole thing. So you could use x is equal to 0 or whatever, depending on what your application is. Same goes with max, right? So you could do np dot max of x, or you could just do x dot max. Okay, so the same axis rules apply here also. Could do x is equal to 0, x is equal to 1. These are all methods of the array x, right? You don't need to necessarily go for the NumPy methods as such. The last thing that would be useful for you is Rmax, right? So same thing here. So that is with respect to useful methods for arrays. And
one method sir has used, that is arg partition. I cannot understand what this method is. I cannot recall in which week he has used. It was arg partition.
okay,
np dot
9, so one of those was, see, week 9 and 10, I am the wrong person to ask. So
it's in week 7, KNN.
It's in KN, is it? Oh, why do you need
partitioning? I mean, it's basically trying to figure out k neighbors, right? So our partition is used to calculate the nearest k neighbors.
Oh, okay. Among all the distances, which are the k?
I mean, you calculate all the distances and then you take the nearest k neighbors. No? So he's used arg partition for that. So it looks like it sorts based on a threshold.
Oh, okay. So I am not used arg partition myself, so I am not like, let me just Do they have any? Does anyone recall the exact use case? How you will?
Sir, instead of args partition, I have used arg sort.
Okay, yes. You start sort and then the first k of that, is it?
Arg sort is also giving the index by sorting them.
Okay, then that's fine. So there is no, it's not binding on you to use a particular method. Whichever works for you is good enough. Is that okay?
So it's using like when you fit a KNN model, KNN classifier model, you have like a feature matrix, and when a new point comes in, you calculate its distance with like every other point. So when you do that, it gives an array of distances, and arg partition like sorts till like the number of k values specify. So top k values like.
Okay, so if you, so let me understand this. So if I give you the X data and a new example, how does it work?
If you give it the like in our case, if you give it the array of distances like maybe 0, 1, like unsorted array of distances, and the k value, the value till which you want like the top k smallest distances. So it
Okay.
will give you indexes of that, I think.
Okay.
Yeah, indexes.
So let's say I have say something like.
I think you should do random because range will be.
Yeah. So what we'll do is I don't know if this is valid function, but let's see. Okay. So I'm assuming that these are some random distances. Now if I give d and say some value like 3, it will give me the top 3, is it?
The index of top 3, smallest thing.
Okay, let me print d also. And then so this is d 0.
Sort the first 3 along.
Okay. I am seeing 9 here. So okay, let me just index dot. Will index work on numpy arrays? Do you have any idea? Does the index does numpy array have index? No, numpy arrays do not have index. Okay, anyway, so this is quite a small. Let's take a slightly smaller array so that. Okay, so I have these distances, and now I run arc partition on these distances for a k value of 3. So it is.
So it gives 4 means 6 is the fourth largest value, I think. If I sort it in ascending order, 6 will come fourth.
6 will come 4, but see if 4, 8, 5 are what? 0, 1, 2, 3, 4. 1 is the index 4.
4 is the smallest. Yeah, index of the smallest is in 4.
But 0, it's 8 is 0 is in the index 8, right? That should have come. So it's giving me 102, right? So if I print,
so it is basically taking the threshold as 3,
okay.
and firstly it is I think it is sorting in ascending order, and then by the threshold everything whichever is in the left is lower than that position, and on the right is higher on that position. In that way.
Nice. Okay. I get your point now. So the whatever it partitions, they need not be themselves sorted in any order, right?
Right.
Okay, that's a good point. So let's just check this with, yes, Spark said let us make it properly random.
A bit like the pivot and the quick sort, I think.
Exactly. Yeah, that's nice. Then a sample. This does not have a size argument, is it? Okay. Hey, what is the
Random dot choice? I think random dot choice also you can use.
no, I just want some 10 randomly or uniform.
I don't think you need to give a tuple, just give like
Just give a
random and 10.
That will work, is it?
Yeah, random.
Randint and then size.
Okay, super. Okay, so let's so let's do randint itself.
10 comma something. It takes tuple. Most probably.
So randint takes a range.
0 to 10 comma something like that way. 0, 10, 19 or whatever comma some size. No, yeah.
Okay, so let's take 0 to 50 as the range of numbers. There's nothing below this 3, right? So everything comes to the right. So let's do 25. Why is
It should be below 10. So 10 is the size. How can it be 25? You have 10 numbers only.
Oh, okay.
So that is, yeah.
So the arc partition will partition the array into first 7. So if I say 7, then first 7
Yes.
and rest. Okay.
First 7 will be lesser than that 7th point, and the right side 3 points will be more than that, more than those, like more than the 7th index.
Okay, nice. Okay. Okay, so if I give the value of the length of the array, I mean it will just end up. Does it end up sorting? No, it is. Okay, so Manish, you are okay with this? Whatever we have been doing so far, right? Is this enough?
No, sir, I haven't understood this so far. So, what it is actually doing?
So it is basically partitioning an array into 2 parts, right? Depending on what index you are giving here.
We have given the index 7.
So index 7 would mean everything is less than everything to the left of d of 7 is less than everything to the right of d of 7. I believe that's what is happening.
It is not sorting.
It is not sorting, right? In the process, it is not sorting, but it is partitioning the array into two parts, such that, as Kaushik mentioned, it's like everything to the left of that pivot value is less than everything to the right of the pivot value.
Like suppose we are trying to find k, and suppose the value of k is 3. Then on the first 3 elements will be
the smallest, the closest in some sense, right? Smallest distance, which is what you want, right? So you want the 3 closest distances from among all your distances. In this case, in this particular array, they are 1, 0, and 0.
So the IND which it is giving, that is not actually sorted, but neither is it in the same arrangement, right?
So if you look at this, it looks like it is it's certainly not sorted, but yeah, it is not even in the same
arrangement.
Yeah. In that case, it would have been 158. Is that what you're saying?
No, sir. I mean, here if I say the arc partition of d comma 3, which means it has to take less than 15 on one side and more than 15 on the other side, right?
No. So it should take all elements which are less than d of 3. So finally, when you not d of 3, sorry, if I have been saying d of 3, then I missed.
No, it basically kinds of sorts it. Even if we are saying that it is not sorted, but if you sort it out, let's suppose we are sorting it in an ascending order, then somewhat it matches of how we are thinking. But ultimately, left side is not sorted after what we are getting.
Yeah, so the best example, the closest is what Kaushik mentioned, right? It does a partition in the quick sort sense. Have you done PDSA?
No, sir.
Oh,
Not
okay.
done.
So what it does is it is separating the array into two halves, into two parts, right? Left and right. So what this is saying is that everything in the left, every element in the left part of the array is less than every element in the right part of the array. That's what is doing.
And the left part is decided by that 3.
Exactly. Yeah.
By the k.
Yeah.
And the 3 is the indice of the, the passed array, right?
It is the first, it's saying, if I'm not wrong, correct me guys if I'm wrong, I think it's saying the first 3 elements should be less than all the other elements in the array.
So basically in the index, we have got 1, 8, and 5, right? So if we see in the distance vector, so 1, 0, and 2 are the smallest what we need actually.
Yeah.
So that is what it is doing.
And 1, 8, and 5 are their locations in that array?
Yes, 1, 8, 5 are the location. Now you can, yes.
I get it now. Okay.
Those are the index.
Thanks. Yeah.
So it returns location, not the numbers itself.
No, it returns location, and then you can get back the numbers by doing colon k or something, colon like that.
You can just pass it to the array, right? So
yes,
we are in fact returning the index in this line, and then we are also using that index to get the elements. So these are the actual elements.
So right? D of colon ind will print those 3, I guess.
Not necessarily colon, right? You just need to do D of ind.
Yes.
Colon is not needed because NumPy allows indices to be NumPy arrays themselves, right? So
right.
Okay, so this I think would have been clear.
Sir, may I add something?
Yeah.
Could you please try doing it without arg? So np.partition, just partition. I think that arg is giving the index. Yeah.
Okay. Let me comment this out. Yes. Yeah. 8, 16, 5 are less than 16, 23, 28, 36. Yeah, you are right. Yeah. So this is much easier. Right?
Yeah. If you need the index, then we'll do arg partition. Otherwise, we just do partition. So that gives it back.
Right. Probably we need the arg partition because we need to find which of the training examples are the 3 closest neighbors, right? So
right, sir, right. We need to find it with respect to y. That is why we are getting the index.
Right. Okay. So that was a. Thanks for asking that question. I also didn't know this arg partition theory. So once we are done with that, awareness of shapes is what we were just talking about, right? So in the exam, we have asked you to return shapes in a very specific manner. So please stick to that. So what is going to happen is if you have asked you to return a vector of shape n comma, then please do that, right? If you return something like n comma 1, even though your answer is correct, you will not be able to pass the test cases, right? Because all our post processing assumes that you return a 1-dimensional NumPy array, and if you end up returning a 2-dimensional NumPy array with the same elements, right, then even though your answer is correct in a sense, you will not be getting the marks for that. Okay, so I hope this is clear. Please, before whenever you write your code, it's good to have these assertion statements wherever you go. So for example, if you have a vector like that, like this, it's good to check if b dot shape is equal to 1, 3 comma. Right? If this is correct, if what you have written is correct, then this will not throw an error. On the other hand, if you do something like this, then it will throw what is called an assertion error. Right? It's basically, this is like a checkpoint for you. It should act like a checkpoint for you. So make sure that your shapes are consistent with what is asked in the question.
So sir, the output shapes should be mentioned.
Output shapes will be mentioned very clearly. We have made it a point to mention that if you're asked to write a function, then in the function's doc string we will be giving you what to return, If it is an array, then we'll tell you what should be the shape of the array that you'll have to return. Okay, so that is awareness of shapes. Yeah, so the other point is about translating math expressions. See, here again, there are two ways to do it. One is to make it easy, the other is to make it difficult, right? So a simple expression, let's say like something like this, right? So W transpose W, which is needed in the case of taking norms, right? Now there are at least three ways to do it, right? One you could say is np dot transpose of W, np dot of np dot transpose of W comma W, right? This is a very complicated way of thinking about this, right? Or you could say np dot of W comma W, most the same thing. Or you could say np dot sum of W into W. The simplest of all, which directly translates from math to code, is W transpose at W, right? Expression 4 is better than all the other expressions simply because it is the closest to the mathematical expression that came before it, right? So let's make sure that all these three are the same. So this is E1, E2, E3.
Karthik, is there any specific use case, like in which place we have to use which method?
No,
we use any of these?
No, so the suggestion from my side is to always stick to this fifth one, right? The W transpose W. So it is, one second, it's saying that all four are not equal.
W power, W star.
Okay, thank you. That is right. Okay, since I started, I'll just go ahead and complete this. Okay, so all four are 14. All four correspond to the square of the norm of W, right? So this is norm W square. But in terms of brevity of expression, in terms of the direct correspondence between the math and the code, please stick to this. Okay. In fact, this transpose itself is not needed. Okay, because if you remember what I said, this is a one-dimensional array. So W at W dot T is the same as W. So, but still, for clarity of the code, if someone is reading your code, it's always better to let them understand what it is.
Be a matrix, right? When we will handle the data set, it won't be a 1D array.
Sorry?
In actual cases, it will be n cross k. It will be a matrix.
So not necessarily, right? Not for all machine learning techniques. Only for some techniques will W be a matrix. For SVMs, for logistic regression, for linear regression, there'll be only vectors.
Yeah.
Okay, so that is regarding conversion of mathematical expressions to their NumPy equivalents. What else do we have? Yeah, the other thing is vectorized expression, right? So for loops, writing for loops is not wrong, but please try to make the best use of vectorized implementation. So for example, if you have an array like, again I'm going back to the same. So if you have an X like this and you want to find the, let's say these are all 5 samples, right? 5 samples in 3-dimensional space. And in the case of k-means, if you remember, you want to find the distance of these 5 points from one vector, let's call that vector V, right? Say it's a 0 dimension, it's the 0 vector, right? Now, you could do for A in range of x dot shape of 0, okay, x of I minus V of x of I minus V, that will give you, this will be what, this will be the distance, right? Euclidean distance between x of I and V, right? And you can assign it to a new array, say distances x, that's the same shape as x dot x of 0, right? So you could do all this, you could do d of I is equal to x of I minus V. Of course, this is not the Euclidean distance, you need to take the square root of this.
That's another thing I would ask. Some places it's some of the graded or I think it was a practice program. It's working without the square root, but when we come to clustering, it works with the square root.
Yeah. So see this. I think that was one error there. The Euclidean distance always has the square root.
Square root. Right.
Okay, but the reason it worked there was in K in where was in KNNs, right? So the reason it works is you are not using the distance to, you are only using the distance as a comparative measure, right?
I agree, but the question should mention that Euclidean.
Yeah. So in the exam and also in the end term exam, please use the actual correct equation of Euclidean distance for the for all your computation, right? It's the square root of whatever, right? Okay, so this is the way, this is one way to compute the distances between x, each element of each row of x and vector V. Okay, so this is a non-vectorized implementation. The vectorized implementation, on the other hand, would be something like this, right? Let's call it D1, this is D2. So D2 is going to be, so remember what we are doing here. This is where your broadcasting will help you. You are subtracting a row vector from each row of your matrix. So you are doing x minus V, right? Now here matrix multiplication won't work, right? So you have to be aware of that. The shape of x minus V is 5 cross 3. So I have to be slightly careful. I need to do x minus V square and then sum it along axis 1 and then take the square root for this to give me the same value as D1, right? So see if we end up with the same value. It is right. So did you all get what happened here?
Yes.
Okay. Others, did you all follow what happened?
Yes.
Okay. Right. So there was a slight difference from this to this, but notice that this is far more compact than this one. But again, in the interest of time in the exam, during the exam, right? If writing for loops comes naturally to you and you are like far more comfortable doing it, please go ahead and do that. It's not like you are going to get brownie points for, you are not going to get brownie points for writing something like this, right? So if you are really comfortable with for loops, please stick to that. But the whole point of NumPy is to learn to do these things, right? Wherever you can.
So we can use any of these, right?
Yeah, you can use any of this. In fact, even going before, right? You can use any of these 4 methods. I was just suggesting what I feel to be the best practice, but you don't need to limit yourself during the exam to one of these. Whatever comes best at that time, given the constraints of time, whatever works for you is good enough.
So sorry to interrupt. I just want to ask whether the GPAs and PPAs are enough for the exam, or should we do any extra coding questions from online?
No, online, not really. And see, if you want to practice, then the best practice is to, if you have the time to recreate these collabs from scratch, right? I mean, it looks like this, it is too much of work, but it's actually not. What I mean is just the training, the learning part of the algorithm, right? If you can sit down and see if you can create it yourself, right? That would be more than enough.
Okay, sir.
Okay, so that, yeah.
Sir, one small thing.
Yeah.
Can you please tell where we can use this? Like here you have just written dot sum along the axis one. So where can we use this notation, and where do we have to use np dot sum or np dot square, this QRT, like that?
Most of the cases this will work. I don't recall a place where np.sum is preferred over. I am
Sir,
not.
if
Yeah.
you have a list, then np.sum would work, but list.sum would not work. That's if you don't have a number array, that's
right. Yeah, other than that, I am not able to think of any place where you would have to use np.sum.
Okay, sir.
Okay, so see, the final point is, I think you all know some important functions like np.maximum, np.concatenate.
Just a quick point. I mean, this np.maximum and np.max are not the same.
They are not the same. Yeah. Yeah. So np.maximum is for two arrays, right? So it will compare the corresponding values in these two arrays and then select the one which is maximum element wise in those two arrays. Right? That is what it does. np.max is given one array, choose the maximum element.
Among all the elements.
Yeah, among all the elements in the array, choose one which is maximum, or if you want to do it along a particular axis, you have to restrict it.
Can you give an example of maximum?
np.maximum, see this relu function, right? If you remember relu in week 12, even though week 12 is not there, still, so if you have, okay, just give you an example like this: in 1 comma minus 1 comma 2 comma 0 and 0 comma 2 comma minus 1 comma 3. This will give you 1 comma 2 2 3 because 1 is, okay, let me change this to 4. So 1 is the maximum among 1 and 0, the first element of the corresponding arrays. Here minus 1 and 2, 2 is the maximum, so 2 will go in here. Likewise, 4 is greater than minus 1, 3 is greater than 0. So element wise, across these two arrays, you make this comparison and pick the one which is maximum.
Even in the SVM loss function.
Right. Yeah, correct. And even in the SVM loss function, the hinge loss uses this. Okay, so np.max on the other hand is just going to operate on this one array and it's going to give you the number 4, right? Just that scalar value 4. np.concatenate, I think you all know. One way you will get an error is if you don't pass the two arrays you want to concatenate inside a tuple, right? Or inside a list or whatever, right? So make sure that you do it the correct way. np.var, very useful function. You already know how it works. So some condition, the result if it is true, result if true, result if false, right? So you make some comparison on some array. If it is true, then what should you do? If it is false, what should you do? Okay, that's the general syntax. What else do you have? Maximum, max, concatenate, var, reshape. I think you're all quite familiar.
Column stack.
Sorry, column stack. Yeah, column stack. np dot column stack. Then you know what?
Excuse me, sir.
Yeah.
So the column stack is the same thing as if we concatenate along the axis equal to 1. Is it the same or is it different?
It's the same as if you concatenate along the axis equal to 1. Yeah.
Could be the same.
It is going to be the same. Yes,
Same,
but
okay.
verify it though, just to be sure. Okay. So the same idea of axis equal to 1 means left to right, right? So if you add the array A here, concatenating it along axis 1 would stick that one column of A to the left of B. So, but still, just to be sure, please verify it.
Sure, sir. I'll verify it once.
Yeah.
One other question that I had is that could you please explain a little bit about that expand dimensions function? What does it do? I mean,
see, this expand dimensions is just to add one more dimension to your array. It is for broadcasting only. It's used typically. So if you have, say, something like this, expand. What is it called? I don't even use this nowadays, so I don't. And then you have to specify one axis.
Come on, one. Yeah, come on. So yeah, come on, one.
It's like reshape only. You can reshape also.
Yeah, exactly. So it's typically done for the broadcasting purpose, right? So if I say this is instead of 3, it's 3, 1.
Right, sir. Yeah.
So when you want to add a column vector to a matrix, then you do this.
Okay, I was just I'm trying to confirm whether reshaping is the same as this or is it different?
Yeah. No, please stick to reshaping because
reshaping. Yeah. All right. That's more intuitive, right?
Yeah.
Yeah. Okay. Sure, sir. Thank you.
Sir, what is the difference between column stack and C underscore?
Column stack and C underscore. I have never seen C underscore. What is it?
Sir, in the NumPy library, there is a function C underscore.
Oh, is it? No, I am not aware of it. I have not used it. So
because sir, for adding dummy features, sometimes I have used C underscore and it works fine.
Oh, then okay. So anything, yeah, as I said, whatever you are comfortable with, whatever you are used to by now, right? That is okay for the exam, from the exam point of view. But as a practice, maybe it might be easier, it may be more advisable to use, say, column stack or even concatenate because it's more general in some sense, right?
Yes, sir. Okay, thank you, sir.
Okay, so any other functions that we have come across? This R partition we learned today, or at least I learned today.
np dot lineal.
np dot. Sorry, np dot.
Lineal, which is used for calculation.
For the norms and all that, right? Yeah, that is true. Yeah. np dot. So you could use lineal dot norm of w, right, for directly getting hold of the norms. Anything else that we have used in our course?
We have P inverse also, sir, for that normal equation method.
Okay. np dot, that is also in the lineal
module, I think. Yeah.
Okay. Anything else? Concatenate, var, column stack, R partition.
Karthik, can you please add this in np dot lineal dot norm in the above while you wrote the norm calculation, the Euclidean distance?
Sorry. Oh yeah, here you mean, huh?
Yes.
Okay, yeah. But this would be np dot lineal dot norm of w square, right? That is what this would be, right? This would be the square of the norm, if I'm not wrong. Okay, this is norm square W transpose W, and this that returns the norm of W. So yeah, I believe that is all. And sometimes you may have to take, if you look at Naive-Bayes models, you may have to take the exponent, or if you want the sigmoid function, you may have to do the, you have to raise things to the e power something. So NP dot, yeah, NP dot log. I think, yeah, that's it's all applied element wise. Please remember that. Okay, so they are all applied element wise.
There's also iterative and function. So it was used, I guess, once only in polynomial transformation.
Sorry, I am not able to hear you. What did we miss out? Is there anything we missed out?
No, it's not actually in NumPy, but it's iterative and functional libraries. They were used only once in polynomial transformation class.
Okay, which library?
Iter-tools and func-tools.
Oh, okay. Yeah. Oh, that part you don't need to worry about, right? So at least for this exam, because they are, there will be no basic linear integration is not part of the syllabus per se for this OPPE, but it's good to know that. Okay, so that's, yeah. Any other questions? So that's all I had. I wanted to cover. Yeah.
There is nothing to do flattening, ravel, unravel, and all that. They've used in many places, but I guess they're all for mostly graphing. I think.
Yeah. Flattening, ravel, unravel. I don't see the need for this OPPE at least.
We won't be massaging any of the data as such, because I think we've used flattening for that MNIST data.
Yeah, flattening for MNIST. Yeah, if you get something, okay, MNIST. Since it's not a part of this, but yeah, but if you want to do that, you have to flatten. Yeah, you are right. Right. So, but even there,
NP dot repeat and NP dot choice.
NP dot choice. Okay, for bagging, is it?
Bagging.
Okay.
Not random dot choice. Is it NP choice?
Correct. Got it. So that is
repeat.
NP dot
repeat.
Okay. NP dot random dot choice, NP dot repeat.
And also, sir, if you can log space, NP dot log space.
Linspace, you're saying, is it? Linspace or log space?
There is log space also, no, sir?
Oh, is it? Oh, okay. Sorry, I didn't know.
I am also not sure. Like I saw some in.
No, there is log space. It will create, the 1, 2, 3, 4 logarithmic values like log 10 of 10, log 10 of 100, log 10 of 1000.
Oh, okay. Okay. Yeah, but np.linspace, good to know. It's used typically we use linspace typically for this thing, right? Plotting purposes. Logspace, where have we used in this course?
Logspace, I think it is in MLP, not in MLT.
Oh, okay.
Okay.
Or what parameter tuning? Hyperparameter.
Yes, hyperparameter tuning, random search, grid search.
Oh, nice. Okay.
Yeah, I must have confused.
Okay. So I'm just removing all the necessary thingies here. Okay.
How much of sklearn in MLT are we supposed to know?
No, sklearn not much. Only the decision tree part requires sklearn, if I'm not wrong.
Correct.
That alone, if you are familiar with, it's enough.
Okay.
Yeah. Any other questions? I mean, that's all we have for today, from my side at least.
Excuse me, sir. May I ask a question? So this is regarding the maximum method. So we have seen it for the vectors, right? And I think you have done it for matrix also, but I just wanted to have that once again so that it's clear. For matrix, how does that maximum works?
Yeah. So it works element wise, right? So if you have, let's say, 20, 5, 4. So we take 10, say you have 5, 2 and Does this have a range? Does this work? I don't know if this will work, but we'll try. No. What are the parameters that the range np.a range accepts? There is no lower limit, upper limit kind of thing, huh?
No, I think there is an upper limit, lower limit, but I don't think there is a step size.
There is, okay. No, what I wanted was the.
No, if you put it on -10, then 30, and then 10.
Yeah. Sorry. You are right. And you can't. So you can't specify the size, right? You're sorry, I forgot. So what do we do? I want 10 numbers. If I do 10 to 20, will I get 10 numbers?
Yeah.
Okay, so let's do something like 5 to 15, 10 to 20. Will this work? Okay, so I don't even know if this is a good example, but anyway, see, here unfortunately what is happening is everything in the second is greater than everything in the first. So let me just subtract some value from this. Then everything in the first. So yeah, I'm not able to get hold of a good example unless I shuffle these.
Just do a random one.
How about okay? So what is happening is you have 9, 18 compared element wise, right? Each element is going to be compared with the corresponding element, and 18 is bigger, so you just insert it there, right? So likewise, second element 19 and 10, 19 is bigger, so you just insert it here. So it's just going to do an element wise comparison across these two arrays.
So in the case of vectors also, that was essentially what was happening, and in the matrix case also the same thing is happening. Only thing is that shape is sort of like preserved.
Yeah.
Okay.
Right?
Understood.
So this will also work if you don't have a matrix and instead you have only a number, because that you can again, that will get broadcast, right? This is what we use in ReLU and the
So
hinge.
if the shape of two matrices are not same, then
I think if they are broadcast, they can be broadcasted. I think it may still be able to pull it off, but I'm not sure. I haven't tried that part. If, for example, here this array is of shape 2, and this is 5 cross 2, right? They are broadcastable, so this works. Now, if I add something like, I don't know what will happen. So again, you're going to get the value error that they are not you cannot broadcast them. So what I do is I end up reshaping it to -1, 1, so they become broadcastable again. Reshape. Right, so as long as you can broadcast them, then the method will work as it is. Okay, but yeah. All right. Any other questions? That's
Karthik, from week 11, what kind of questions might come? Because only two concepts are there in programming. One is centroid and another is silhouette.
So you may be asked to do the entire k-means algorithm from scratch.
Okay.
Right, so you must be prepared for that. Since k-means is not too hard from the theoretical point of view, it's just repeatedly you do certain things, right? So, or you might be asked to compute the silhouette coefficient, things like that.
Sir, for silhouette coefficient, we will use the same formula, na?
The correct formula, whatever is the correct formula, please use that. In Wikipedia, the correct formula is given, right? What is there in the slides is wrong.
Okay, sir. And one also small thing from week 11 only. there is a practice assignment question where it says to find the centroid A, find the centroid of in bracket it is given A comma B, and A or B are separate vectors. So I somehow after doing a lot of hit and trial, I got the correct code, but what is the motivation behind this question? What is it trying to do? I cannot understand. If you can explain that part.
What is the question? It's asking you to find the centroid, and it's giving you they have given you two vectors, is it?
Yeah. So my question is like whenever I find a centroid, I find the centroid in that vector. So if I have, let's say A is a 10 cross 2 matrix and B is also a 10 cross 2 matrix. So I will find the centroid for A and find the centroid for B. That is how I find the centroid, like in K-means
Okay.
cluster.
I don't know that. See, that question is, I think, badly phrased. So, centroid, if you are asked to find the centroid, right? First of all, you must be given some kind of cluster assignments, right? Otherwise, you can't find the centroid. So, see, whatever question, if at all it comes up, will regarding K-means, it will have these things, right? First, you must be given the matrix X, which is of shape n comma m, right? This is a constant in all our algorithm, right? N samples, n features, that matrix you must be given. Then you must also be given the assignments, right? Which point belongs to which cluster. Unless you are given these two data points, or rather data items, you can't compute the centroid. So,
Okay.
right? So that question was not framed correctly.
Okay. So there is nothing to worry about this question.
Yeah, what you'll, I mean, centroid of A comma B doesn't even make sense, right? As a question.
Yeah. Like you can compute it, but I cannot understand the purpose of this question.
Yeah. So such vagueness and ambiguity will not be there. It will be more clear in the exam.
And Karthik, what kind of, regarding 5 to 11, I have just a few doubts and regarding what kind of questions will you ask from naive way, like week 6. Like from scratch, something we have to calculate like likelihood and all those things.
Yeah, so naive base from scratch you must know, right? So how do you, starting from, obviously what type of naive base will be given to you, but let's say it's Gaussian naive base, then if you are given a matrix X like this, then you'll have to initialize your mu matrix, you'll have to initialize your sigma matrix, right? And you have to do the parameter estimation by following MLE. I mean, MLE and all you don't need, right? So you know the final form. For mu, you have to look at all the data points.
That's what I'm doing. I mean, I just have to, use like the vectorized form for that particular thing, right?
Yeah, that will work, yeah. Right? So, but you must be aware of that. Yeah.
Sir, what are the important ML algos for tomorrow? Because not every ML algorithm was done in the solve with instructor session. So which one should be focused on?
In everything from week 5 to week 11, right? As a responsible instructor, that is what I should be telling you. I can't tell you what you should focus on because that would be the wrong thing to do from my side. Right? So unfortunately, I can only reveal this much. Right? Please focus on everything from week 5 to week 11. Some weeks are light, right? Week 7 is very light. Yeah, only Kane, and week 11 also is kind of light. 5, 6 is a bit heavy, so 6 maybe you'll have to spend some time.
Yeah, 6 is a bit of troubling there.
Yeah, but in week 6, you must remember that the formula is the same for all the naive base, right? You have to look at the vector X, the data matrix X, look for all those points which have label W equal to class C, right? Take the mean of them along axis equal to 0, right? You're doing from top to bottom. This is the mean of mu jk, right? So this is for class C, this is your mean vector, right? So this standard form applies to almost all naive-Bayes techniques. Look for all those points which belong to a particular class, find their mean, that will be your mean estimate. Okay, so yeah, I know it can be hard, but you'll have to work on it. Okay, any other questions? If not, we will close.
Hello.
Yeah.
Yeah, I'm asking that in MLP they will be providing a sheet for all these things. I mean these formulas and all those things. So can we expect the same in MLP?
No. See, in MLP we are not giving you formulas, right? We are only giving you I think we are giving you what the APIs, where they are found and things like that, right?
Like.
Yeah. So in MLT, sorry, we are not going to give you that because NumPy is kind of, see, we have more or less listed down what all you'll be using, right? And some of these like log space and repeat, you won't be using it even that often, right? The most common things will be say column stack or np.var, np.max, right? So these you can remember, right? It's not too hard. So
No, I'm asking what about these regarding Python libraries? I'm asking about the mathematical formulas.
No. Mathematical formulas, for one thing you can do is, see, Kaushik has shared one document in Discourse. You can refer to that. That has the consolidated list of formulas. So that may be of some help to you. But more than that, during the exam, we won't be providing anything. Okay.
Sir, will solving the programming assignments be enough? What we have done, practice programming and edit programming to pass this exam?
Yeah, as I said, that is good. But what you can add to that is code as many algorithms from scratch as you can. Right? So, see, if you know how to translate mathematical expressions to NumPy, that's all you need to know. Okay, anything else? If not, we can wind up.
Yeah, thank you.
Okay, then all the best for tomorrow's exam.
Thank you, sir.
Yeah.
Thank you so much for your help. It's very
Thank you, sir.
Thanks, everyone.
Thank you, sir.